Hi everyone. We are from PKU Data Lab at Peking University, and I am Yujie Wang. And next to me is my teammate Xinyi Liu. And we are very honored to be here at PyTalk Day China 2025 to present our system work. Our system is called Hetu Galvatron, which is an automatic distributed training system for efficient large-scale foundation model training. So I will first introduce some background and illustrate the core system design. And then I will hand it over to my teammate to introduce the detailed system features and evaluations. Okay, so first, in recent years, we've seen rapid progress in large language models, or called LLMs, like ChatGPT, Gemini, Cloud, and DeepSeek. These foundation models have demonstrated strong performance across language, vision, audio, and even multimodality tasks. These foundation models follow the scaling laws, that is, increasing the model size and increasing the data volume leads to better model performance. However, as the model size grows, the memory of a single GPU becomes insufficient. So this makes distributed training across large GPU clusters really important. So to conduct distributed training, there are different parallelism strategies. They will shard the model or the data along different dimensions and distribute them on the cluster. For example, tensor parallel and pipeline parallel shard the model parameter. Data parallel shard the data along the batch dimension, and sequence parallel shard the data along the sequence dimension. And all of these strategies can be further combined together to hybrid strategies. Okay, so besides the diversity of the parallelism strategies, the training workload are also diverse. For example, different model types and different model configs and different sequence lengths, they will all cause the diversity of the workload. And also, when we train the models, we will have different clusters. For example, they will have different architecture, like NVIDIA Hopper and also ASIN NPUs. And also, they will have different computational capabilities. Also, they will have different memory and different bandwidth configs. So this makes the finding the optimal parallel strategy on every workload and in each case is really difficult. So this will usually require significant manual tuning. So in our system, we want to address these challenges. We developed a fully automatic and fine-grained distributed training system called Hetu Galvatron. So the target of this system is to remove all the need for manual tuning in parallelism optimization and deliver the efficient large-scale training out of the box. So first, I will walk you through the system design. The key design objective of Galvatron includes two parts. First, we want to provide automatic parallelism optimization. It will require no manual intervention. And second, we want to provide enhanced system efficiency, choosing the optimal and most efficient hybrid parallel strategies for each case and on each workload. So to achieve these targets, our system explores a large strategy search space, and it will support fine-grained hybrid parallelism. And also, Galvatron includes an efficient search engine to realize the automatic optimization. So first, let's talk about the parallelism search space. Our system will incorporate most of the mainstream parallel strategies, including DP, which is data parallel, and SDP, which is called, in our system, it's called sharded data parallel, and also known as 0, 1, 2, 3. And also model parallel, including tensor parallel, like Magnetron style TP, and pipeline parallel, like G-pipe, pipe dream flush, or also called 1F1B pipeline. And also, we will incorporate sequence parallel, like Magnetron style SP and Ulysses style SP. And besides, we will also incorporate activation rematerialization techniques as some of the unique or a different parallel dimension. Actually, the activation checkpoint distributes the memory across the time dimension, and activation offloading distributes the memory across the CPU. So they are kinds of parallelism also. And we are also currently working on context parallel and expert parallel, and they will be released soon. And all of these parallel dimensions can be further combined as hybrid parallel strategies. So this will make the search space really large. And the second one is one of the highlights of our system, which is called fine-grained hybrid parallelism. This is really important, and this is the main performance gain of our system. So I will explain why fine-grained hybrid parallel is really important. This means that in Galvatron, each layer can use different parallel strategies, and it is designed to support layer-wise hybrid parallel in the beginning. And firstly, different layer can have distinct layer structure and layer workload. For example, multimodality model have multiple type of layers. And also in 1F1B pipelines, different stages have heterogeneous memory consumption and different layer workloads. And also in MOE models, we know that attention layer and MLP layers are really different and they have different workloads. So these workload heterogeneity across the layers leads to distinct parallel preference, which means that different layers prefer different parallel strategies. So this motivates us to do the fine-grained parallel in our system. And secondly, fine-grained parallel allows us to trade off better between the memory and the time. So for example, here we have two different hybrid parallel strategies. Strategy A may be fast, but it exceeds the memory limits, while strategy B is slower, but it is memory safe. So if you use strategy A, it will exceed your GPU memory limits, but use strategy B, there will be a waste of the memory. So in Galvatron, we have the layer-wise fine-grained parallel system, hybrid parallel, and it will let us to combine these two different strategies across the layer and achieving both memory and speed efficiency. So the fine-grained parallelism is the key reason why our system often outperforms existing systems. Okay, so to achieve the efficient automatic optimization, Galvatron first designed accurate cost modeling for distributed training, and it will combine the strength of the profiling and the simulation. And I will leave the details of this cost model to my teammates. And then we will also design an automatic and efficient search engine based on search space decomposition and pruning. And it will be powered by dynamic programming-based optimization core, and we will find the best configuration efficiently. And finally, this page gives the system architecture of He2 Galvatron. Firstly, the profiler will capture the necessary hardware statistics and the model characteristics. And then the search engine provides accurate cost modeling and finds the optimal parallel strategies automatically and without any human intervention. And then the runtime engine will execute the search fine-grained hybrid strategy for the efficient training. Okay, so now I will hand it over to my teammate to introduce the details of our system features and some of the evaluation results.
Hello everyone. I'm Xinyi Liu. Next, I'll dive into the details of Galvatron and its key features. PyTorch native auto-optimization, versatility, and user-friendly. First, let's start with PyTorch native. A core strength of Galvatron is its fine-grained hyper-parallel runtime, which is built entirely on native PyTorch. Users can take a standard single GPU PyTorch training model, and Galvatron will transform it through several key steps. First, it replaces layer with specialized models that support tensor and synchron parallelism, while also incorporating fused kernel for enhanced efficiency. Next, these models are organized into a sequential model and partitioned into different pipeline stages. Finally, PyTorch native wrappers like FIDPs and checkpoints are applied to each pipeline. This flexible architecture allows different models to employ diverse parallel strategies, achieving true fine-grained hyperparallelism. Importantly, the module granularity is highly adaptable, ranging from field transformer layer to individual attention or MLP layers. Next, we are going to talk about auto-optimization. As mentioned before, Galvatron features an efficient auto-optimization engine based on cost model and search engine. We developed a precise cost model by balancing profiling overhead and simulating accuracy. During profiling, Galvatron gathers essential discretized data points, such as bandwidth under different volumes, computation times, and memory usage under various sequence lengths and batch size. This is crucial because runtime implementation, such as the use of fused kernels, will significantly affect computational times and memory efficient, making the simulating with standard formulas inaccurate. In the simulating phase, Galvatron phases collect data points into continuous modeling curves, then it simulates execution times for different parallel strategies and provide accurate time and memory estimates. Notably, our model also considered the slowdown caused by the combination and computation overlap, as combination also utilize SM resources. To make the cost model more accessible, we have developed a visualization demo. As shown on the right, this tool offers an intuitive way for users to compare memory consumption across different parallel strategies. Galvatron also offers an automatic and efficient search engine, which constructs the search space using decision trees and prunes ineffective strategies based on several observations and takeaways. When they integrate the cost model with parallel strategy and feed them into the serving algorithm. This algorithm is based on enumeration and dynamic programming. Specifically, the dynamic programming approach is similar to a knapsack algorithm, where we need to find a parallel strategy for each layer. The memory and time consumption for different parallel strategy can be viewed as the capacity and value of items. Furthermore, the enumeration part can be accelerated using multi-threading, ensuring a rapid resolution. As for versatility, Galvatron supports a wide range of model architecture and adapts to multiple hardware backends, including NVIDIA GPUs, ASIC NPUs, and high-end DCUs. As for ASIC hardware, we ensure seamless integration through Torch NPU. Finally, let's explore user-friendly. Users can convert a standard single GPU training model into a fine-grained hyper-parallel model with only two interfaces, one for obtaining parallel strategies and another for model modifications. Minimal changes are needed for existing training code, and comprehensive documentation and examples are provided to get user up and run quickly. To further enhance its ease of use, Galvatron also adapts to other frameworks data loader, allowing direct use of prepared datasets. Additionally, we have innovated checkpoint management by storing checkpoint at layer granularity. This approach ensures checkpoint compatibility with any parallel strategy. We also provide convenient scripts for converting checkpoints to and from Hugging Face formats. So as for experiments, on NVIDIA clusters, we test different large language models across different GPU types and cluster size. We compare its performance against manually tuned Magnetron and DeepSpeed. While Magnetron and DeepSpeed each have their respective strengths and weaknesses across clusters and models, Galvatron consistently adapt to different cluster and models characteristics for superior efficiency. Galvatron is effective on ASIN cluster 2. On a 256 class 910 B4 cluster, Galvatron achieved an 80 speed improvement over ModuLink 1.1, demonstrating the benefit of fine-grained parallel strategy in optimizing limited memory for better performance. We also performed accuracy tests to confirm the correctness of Galvatron. So in summary, Galvatron is an innovative PyTorch-based system that delivers a comprehensive fine-grained automatic parallel training solution. By tightly integrating profiler, search engine, and runtime, it achieves state-of-the-art throughput. And we have established extensive collaboration with partners in both academia and industry. In the future, we will continue to develop in Galvatron. Our roadmap includes incorporating more advanced parallel strategies such as context parallelism, X-ray parallelism, and the latest torch FSDT2. We will also explore fine-grained rematerialization, support more models and attention sets, and optimize post-training workflows. For the search engine, we aim to enhance the search efficiency, reliability, and visualization features. So that's all. Thank you for your attention. You can find our repository at the address shown on the screen or scan the QR code. We sincerely welcome you to explore the Galvatron. Try it out and share your valuable feedback.